welcome to the lecture An Introduction to Large Deviations. And today we will finish the proof of the Schilder's theorem, the large deviation principle for Brownian motion, which we formulated last time, and also we started that proof last time. And there is are still something that we didn't have time to discuss, and actually this lecture today will be devoted to the finishing. Mm, so the proof, and in particular, we will talk about the exponential tightness, and we will talk about the variational, some variational equality, which appeared last time. But we will do everything step by step. So let me first of all recall the formulation of the Schilder's theorem, recall what we proved, where we stopped, and then we will continue. The theorem is formulated as follows. It is theorem 7.1 in the lecture notes that is on the course webpage. Maybe first of all, the name of the topic. It is 7.1, Schilder theorem. And the theorem is formulated as follows. 7.1. It is, we say that, let W be a standard Brownian motion. In R. Standard, it means that it started from 0 and has diffusion rate 1. And we also define the family W epsilon of t that is equal to square root epsilon W of t for t from 0 to capital T. And for epsilon that are positive, then the family W epsilon satisfies the large deviation principle in the space C0, 0t. It is the space of continuous functions from 0t to R started from 0, means that the function at 0 is equal to 0. And or with the good rate function, that is equal to IF is is a 1 over 2 integral from 0 to t f dot square of t dt, when f is absolutely continuous with square integrable derivative. I will not recall what it is. We already considered this space a few times, and plus infinity otherwise. Okay, good. Now about the proof. Last time we show the lower bound. So we have proven that that for every G open in the space of continuous functions, one has then the lim info epsilon goes to 0, epsilon logarithm the probability that W epsilon belongs to G is larger or equal than minus infimum f belongs to G, I of f, This we call the lower bound. The lower bound. Lower bound. And we also starting proving the upper bound, but only the upper bound for compact sets, which should follow from the following inequality. So therefore, for let me say that as follows: for upper bound, we let me first of all write that upper bound to recall it for every f closed in C0, 0t, the lim sup epsilon goes to 0, epsilon logarithm, the probability that W epsilon belongs to f is less or equal than minus infimum I of f, f belongs to f. As I already said, this we proved, and that inequality we want to prove. And to prove that inequality, we have to show, or we divided the proof of this inequality in a few steps. First of all, we showed, first of all, we want to show that for every f that is continuous function, we have that limit r goes to 0, the limit supremum when epsilon goes to 0, epsilon logarithm, the probability W epsilon belongs to the ball of radius r and the center at the point f is less or equal than minus I of f. And then with this inequality, using the proposition 6,4, we get that the upper bound holds for F compact. And then we will get, or this is weak large deviation principle. That also we discussed it, and also we know that if we prove, and then next we want to prove, we need to prove that the family W epsilon is exponentially tight. What it is now, it is not so important. We will recall the definition a little bit later when we will discuss the exponential tightness. But now for us, it is important to know or to remark that having the weak large deviation principle plus exponential tightness, we will get the upper bound. The upper bound for F closed. And this will imply the proof of the theorem. Now, about the previous time. The previous time we finish, discussing this inequality on the following stage. Last time we showed that for every f from C0, 0t, the limit r goes to 0, lim epsilon goes to 0, the lim sup, epsilon logarithm, the probability W epsilon belongs to the ball. Then using the Cameron-Martin formula, and integration by parts, we could show that this is less or equal than the supremum over all functions h that belongs to continuously differentiable functions on 0 t to r of here should be minus of the function some function phi of h comma f where this function phi of h comma f is defined as let me find the definition. It is defined as follows. It is h of t f of t minus integral from 0 to t h prime of t f of t dt minus the 1 over 2 the integral from 0 to t h square of t dt. I will not recall you how this function appeared because last time we spent a lot of time about that, and also if you want to see more or recall, you need to like see the video which is available. Maybe everything what I want to say is that this function appears when you apply that, when you do the transformation on density, apply the Cameron-Martin formula or Girsanov theorem. And then the power which we will see in the exponent, it will be this function of phi multiplied by, it seems, by 1 over epsilon. And now today we want to show that this will be equal to minus I of f. So actually, it is a goal for today. And the second, so okay, let me write that as follows, that today we will show that supremum of this function phi hf over the continuously differentiable function. You see, we need to assume that function is differentiable because we have here the derivative of the function f is equal to I of f, where this function, the rate function, is defined like that. And the second, what we want to show, it is the exponential tightness. Second, exponential tightness. Of the family W epsilon. Epsilon goes to 0. Oh, or epsilon positive. Okay, good. Then let's start with the proof of this variational problem, let's say like that, because you actually need to investigate the function capital phi on that on maximum or supremum, and you need to show that the supremum is exactly the rate function I of f. Oh, then the section will be, it is a section 7.3.2 in the lecture notes, a variational problem. And so let's recall once again, maybe not writing, just copy that. We want to show that where the function phi is this function. And to prove this equality, I want to show you that actually this variational problem is not so strange. In particular, if f is regular enough, then this variational problem can be solved very easily. So first of all, remark that that uh, that um, that for f that is twice continuously differentiable function that started from 0. Then because you remember that we consider the large deviation principle in the space of continuous functions started from 0. Twice continuously differentiable. Remark that for f, the variational problem is not complicated. Let's discuss this why. Okay, take f from C to 0t. And then let's consider the function phi of h comma f. It is equal to, I want to copy that function again, minus integral from 0 to t, h prime of t, f of t dt, and minus 1 over 2 integral from 0 to t h square of t dt. And now let's remark that this part, what you can do, you can take this function and move it inside the differential. You will have df, dh, and then you can integrate by parts. Here, all functions are continuous. Then you can apply the integration by parts formula. Also, functions are differentiable. Sorry. So therefore, the integration by parts formula gives you that it is the integral from 0 to t h of t f prime of t dt. It is that part. And then you will have minus 1 over 2 integral from 0 to t h square of t dt. And then after that, you can use the inequality that I believe is well known for every one of you, that and actually it is the Cauchy-Schwarz inequality. I think it is AB is less or equal than A squared divided by 2 plus B squared divided by 2. But actually, it follows easily from the fact that a minus b to the square is non-negative, and then when you open the bracket, then you will see exactly that inequality here. It is for a comma b from R. Therefore, using this inequality to the first integral, you will see the following. You will see that the first integral is less or equal than so integral from 0 to t, and then you apply the formula to the product of functions. Then you will see 1 over 2 h square of t dt plus 1 over 2 integral from 0 to capital T f prime of t square dt minus 1 over 2 integral from 0 to t h square of t dt. And you see that that integrals are cancelled. Now, then it is 1 over 2 integral from 0 to t f prime of t square dt, that is I of f, right? And this is true for every h that is continuously differentiable function. So therefore you get immediately that this supremum that we have h for continuously differentiable functions of the function phi h of f is less or equal than I of f. But now just let's take h that is equal to f prime. If you take h that is equal to f prime, what you will see that your function here f, if you take this h, it is equal to f prime, you will see and apply the integration by parts formula. You will see here f prime, you will see here f prime to the square, and then it will gives you the integral 1 over 2, the integral from 0 to t f square f prime square dt. That is exactly I of f. So therefore, for this particular h, you see that the supreme that this function is exactly I of f. So therefore, there is no choice. The supremum must be equal. Then you get the equality. Because this you see, because that maximum or supremum are reached on the function h that is equal to derivative of the function f. And also it explains you why we assume that the function f must have two derivatives, because you remember that functions h must have one derivative, and since h should be equal to f if when you take it equal to f prime, so therefore you need to have one additional derivative. If the function f is not twice continuously differentiable function, then of course you need to be more careful, because for instance you cannot integrate by parts. And therefore you cannot get so simply this bound which we had here. You also cannot take the function h that is equal to derivative of function f, because it can happen that the derivative does not exist. And so on. And somehow we need to like fight with that problem, which is here. And for that we will use the functional analysis. I would like to, in this section, I would like to formulate, because it is done also in my lecture notes, this variational problem, which we want to obtain here. It is formulated as the proposition. There is a question whether we estimate these C2 functions. Probably this is a question about for the general case. And no, we will not approximate functions by twice continuously differentiable functions. We will do that differently. We will go via the representation theorem and so on. We will use some like approach from the functional analysis, which I found quite nice to show you it. You can think whether it would be possible to approximate the functions by twice continuously differentiable functions somehow, but you should be actually careful because I mean, you not only to approximate the function itself, but also you need to approximate the derivative of the function, because you see that the rate function has a derivative. And when you do the approximation, you also want to see that this I of f also will converge. So therefore, about the approximation, I think that it is not so easy to realize that idea. But anyway, thank you for the question. Then proposition. 7, 10. For every f from C0, 0t, we have that the supremum, let me copy that again. We have that this supremum is the rate function, where the function, where this f is given by that formula. Okay, then proof. And to prove, it would be simpler for us to make some notation, or to denote the supremum, just to avoid writing every time writing supremum, just j of f. And then our goal will be to show that j of f is equal to I of f. Then we first prove the equality for the case when this supremum is finite. J of f is finite. So let's assume that function f, it is a continuous function started from 0, such that this supremum is finite. And then let's show this equality for such a function. Our goal will be to show that function is absolutely continuous, and the equality is, and this supremum actually is equal to this integral with this derivative in the definition of absolute continuity. And to show that equality, let's do the following trick. Let me take this j, yeah, here. I will consider it here. And then here, let's replace h by theta h. For theta, for theta from R. Note that C1 space is a linear space. So therefore, when you replace h by theta h, nothing will be changed in the supremum because the domain under which you compute the supremum is not changed. So therefore, we have j of f is equal to supremum, and then it will be h belonging to C1, 0t, and here we will have theta h of f, right? And then, after then, let's note that for h from C1, 0t, the function phi that is, I'm sorry, the function of theta that is the function of phi of theta h comma f. And we can write this function as follows. It is like theta, because let's see what the function f is. So here in this function, we want to put theta everywhere. We put here theta. It means that theta is here, here, and here will be theta square. So therefore, for us, you see that here theta appears like in power 1, and then we can write this as theta multiplied by this function, which is here. We will give some special notation for that function, and then you will have this theta square. Then you will have g, I'm sorry, you will have g of h comma f minus theta square of 2 integral from 0 to t h square of t dt, when this function g of hf, it is ht f t minus integral from 0 to t f prime of t f of t dt. And then look, the function which is here, it is for fixed h, it is a parabola with respect to theta. Moreover, this parabola, you see that here this theta square is with minus, so therefore the parabola looks like that. So it has a finite maximum, and this maximum is reached. So note that the maximum of the parabola is reached at the point theta h maximum. We will denote that point like that, because that point of course depends of h. When you change h, then the maximum is changed. Then of course, yes, then the maximum theta is changed, or arc maximum more precisely. hf divided by integral from 0 to t, and you will have, let me write that, follow this divide, I will write like that, divide by the integral from 0 to t, h square of t dt. And then let's see what happens then consequently. We have that this j, that we have this equality for every theta which you like. Copy. It is the supremum that h belongs to C1, 0t, and then you put here phi of theta h maximum of h comma f, which implies that jf, it is when you like take this this object, when you put here the maximum point, you will see that it is that it is 1 over 2. It is exactly the maximum of that parabola. Supremum h belongs to C1 0t. And then you have g square of hf. And then you have the integral from 0 to t, h square of t dt. And now it is really, so this equality which we have here, it is much better. And let me explain why. Because look, what actually you see here. Here you see the L2 norm of the function h with respect to which you compute the supremum. And here you see g square, but this g which is here, it is linear with respect to h. Let me, so here, let's consider, oops, I'm sorry, I made a typo here. Here should be h, right? So because as I said, this term comes from that term, and this is h prime. So therefore, you have that it is linear with respect to h. So then what you see here, your functional square divided by the norms square. And then you take the supremum. And this is the norm of the linear function. Therefore, we can like play around this formula to use some known facts from the functional analysis. But actually, from now, it should be clear for you in which direction we have to move. Actually, we need to define the space, some say Hilbert space or Banach space, or some Banach space with the norm. We need to define some linear operator, and then we will see, we need to like see what we actually can get from that. So we consider C1 0t as maybe I will go to another page. And we consider that space C1 as a linear subspace of L2 0t, which is dense. Is dense in L2 0t. Let's also note that the norm of h on this space L2 is a norm square is defined as the integral from 0 to t h square of t dt. So therefore, exactly here you see the norm h square in L2. Okay. And C1, it is a linear subspace. And let's also take so the linear operator, define it like so. This, let's say j of so gfh, it is defined as g of so this function g h comma f for h that belongs to C1 0t. You have a linear operator now on the dense subspace of this L2 space. And let's note that the supremum over h from C1 0t of g, this g f h, if I put the square, so the absolute value, and then I will put here norm h. So it is, so then this is bounded. Why it is bounded? Because when you take the squares here, it is exactly what is written here. And it is finite, so therefore without square also it must be finite. So therefore this linear operator is bounded on the dense subspace. But you know from the functional analysis that in that case, GF can be extended to a bounded, or maybe to the bounded linear operator. Maybe it's better, yes, bounded linear operator on L2, 0. But what we know about bounded or continuous linear operator, I'm sorry, not linear operator, linear functional. It takes the values are numbers, right? Functional. But what we know about linear continuous linear functionals on a Hilbert space, we know that each functional can be defined as an inner product with some element. So therefore, this implies it is called the Ries representation or Ries theorem, I would say. So the Ries theorem implies that there exists a function which we will denote by g, which of course depends on f, because you see that this f here is fixed, and this function depends on that f. This function is from L2, 0t, such that gf, maybe also again I will copy, so since we will develop this idea further. Cut them. Okay, we said that it can be extended, and yet using the Ries representation, there exists f such that gf of h. Also, this extension also I will denote by g. It is the integral from 0 to t gf gf of t multiplied by h of t dt for every h from L2 0t. In particular, this g that is defined for let me see what I wrote first. Yes, hf, first of all, h and then f. It is the integral from 0 to t gf of t h of t maybe let's do that better. I don't want to write that twice. You remember that this we define it as this function g, but let me write this function g what it is. The function g is equal to here. Let me copy this function. That is this curl g, and it is equal to integral from 0 to t gf of t h of t dt, and this is for every h from this subspace, dense subspace C1 of L2. And it is nice property, it is nice equality. Since it is satisfied for every h, you will have a homework exercise which will claim that by homework exercise you will get it for the next homework. You will need to show that this implies that function f is absolutely continuous, and its derivative is equal exactly this function. G. It is not complicated to show. You also will get some hint for the solution, and I'm sure that you will be able to figure out in that question. But now for me, it's important that this equality, which we obtained here, it implies first that the function is absolutely continuous, and we know precisely what the derivative is. This derivative is equal to z. And by the way, let's note that this is from L2, 0t, because that element, because this is an element of L2. So therefore, the derivative is the integrable is integrable with square. In particular, this implies that when you take the function g h comma f, it is, you remember that this, so this is your function g, and it is the inner product, but then we can use the Cauchy-Schwarz inequality, and the Cauchy-Schwarz inequality implies that when you take here square, you will have that it is less or equal than integral from 0 to t gf square, but this gf, it is f dot square of t dt multiplied by integral from 0 of t h square of t dt. That is equal to 2I of f, because it is the first integral is I, and then you will have this integral from 0 to t h square of t dt. But let's see what actually we obtained. We obtained that function, we estimated by some constant, and then we have this object here. So when we come back to our notation g, and when we will use the estimate which we obtained, we can estimate that, so this g square by what we obtained, and then you see you need to divide that by the integral, you need to divide by 2 and compute the supremum. So therefore this g of f, so from this inequality you have that the g of f is less or equal, and then you take, as we said, you divide this by that integral, by 2 also divide, and then you compute supremum. But you see that everything is, for every h it is estimated by I, so it is I of let's summarize or write this once again, that we got that I of f is less or equal than I of f that is okay, good. It is like that one. And you see that here we didn't use everything because let me recall you that this is g, right? But you see that when we estimated this g square, we use the Cauchy-Schwarz inequality, and here we wrote it is less or equal, so, or we wrote that here it's less or equal than the product of integrals. But you know that the Cauchy-Schwarz inequality gives you also the equality in the case when one function is proportional to another function. So therefore, you can take the function h from L2 that is proportional to the function g, and then you will have the equality. Okay, you cannot take, so here the h has to be a continuously differentiable function, and you then can, if this function is not continuously differentiable, then you cannot take h that is proportional to the function g, that is g multiplied by some constant. But you remember that your space C1, the space of continuously differentiable functions, is dense in L2. So therefore, the function which is proportional, for which you have this equality, you can approximate by continuously differentiable functions. So therefore, this inequality actually you can approximate by functions, which will give you the equality. And this is the reason that you will have the equality I of f. So, and it is how you prove the equality. So if, once again, if j of f is finite. Then the second case that we want to consider here to finish the proof of the proposition, let's assume that I of f is finite. then we know that the function f is absolutely continuous. And since the function f is absolutely continuous, you will have also the exercise as a homework exercise. It will be another part of the previous exercise that we used. It will be formulated as follows. Let the function f be absolutely continuous. Show that for every h that is from c0 0t, one has that ht f of t, that actually it is the function g h f, minus integral from 0 to t h prime of t f of t dt is equal to the integral from 0 to t h of t f dot of t dt. Now also you have the integration by parts formula. In that case, if f is absolutely continuous, so therefore having this, what you can get, again, considering this functional, I mean, which is given by this functional function g, you can write it as this integral, so of this form. But now your function is not only absolutely continuous, but your density is L2 density. So therefore, in this Riesz representation theorem, the function g f that we obtained the last time, it will be equal to f dot, that is from L2 0 t. And of course, this will imply that also g of f will be less or will be finite. Less will be finite because this g of f, you see that it is defined as so via the norm of this function g, and now you see that this g can be represented as the inner product of some function L2 function with the function h. And since the inner product is a bounded linear functional, so this g will be finite. But since g is finite, we already proved for that case that in that case you have the equality when g is finite. So therefore, this implies that g of f is equal to I of f. And this finishes the proof of the proposition. Because if j is finite, then we prove the proposition. If I is finite, we also prove the proposition. And this is enough for all possible cases. Because, for instance, if g is infinite, is equal to infinity, that I must be equal also to infinity. Because if it is not the case, then it means that I is finite, and it must imply that g is finite, but it is not. And the same consequence when I is infinite, that also g must be infinite. Because if g is finite, that it is equal to I, and I must be finite, that also gives you the contradiction. So therefore, these two cases covers all possible cases that gives the proof of the proposition. Okay, so we have finished. And we show that this j of f, it is exactly I of f, which gives the upper bound. Let's go back. This gives this upper bound here, and this part is already obtained. Now everything what we need to discuss to finish the proof of the Schilder theorem is the exponential tightness of the Brownian motion. Good, then exponential tightness. It is section 7, 3, 3. Exponential tightness. And to show the exponential tightness, I would like to recall you one of the exercises which you obtained for homework. And this exercise was looked as follows. I need to open it. I do not remember. It's in that exercise of homework number 6, I think. Yeah. Oh, it was problem sheet. Sheet 6 and the exercise number 2. Exercise number 2. It was that let you have that psi epsilon is a family of random variables. A family of random variables in R such that there exist constants lambda positive and kappa positive such that you have the estimate that expectation of e to the power lambda epsilon of absolute value psi epsilon is less or equal than kappa 1 over epsilon for every epsilon larger than 0. Then show that this family, that psi epsilon, is exponentially tight. What does it mean? And here probably it is a good time to recall the definition of exponential tightness. It means that for every beta that is positive, there exists k compact in the space in which you formulate the large deviation principle, such that the upper limit epsilon logarithm, the probability that psi epsilon does not belong to that compact k is less or equal than minus beta. And the proof of this proposition is not complicated. It seems that here you need to use the Chebyshev inequality to immediately come to that estimate. And the fact that actually the ball in the closed ball in the space R is a compact set. So therefore you can estimate the probability that, that the random variable is outside of the ball. It turns out that you have a similar property or a similar, the similar property for the tightness in the space of continuous functions. But now you know that both in for continuous functions are not compact sets because the space is a Banach space which is infinitely dimensional space. So therefore their balls cannot be compact. And then you need to be a little bit more careful because you just cannot like do the estimate via the Chebyshev inequality of the probability that the ball, that the Brownian motions or family of Brownian motions do not belong to the ball, so is small, and then you will get the exponential tightness. Exponential tightness will not follow from that. But you know in the space of that you know the Arcela-Ascoli theorem for continuous functions, which in particular say that if the functions are uniformly continuous functions, then this set is relatively compact. But this property, it can be obtained from the control of the Hölder norm of functions, of continuous functions. So therefore, if you can uniformly control the norm of the Hölder norm of continuous functions, then you can show that that set is relatively compact. So therefore, to formulate the analog of this inequality for the space of continuous functions, it is not enough just to consider, say, the norm of your functions. You need to put here the Hölder norm, and then you will be able to formulate a similar inequality or similar property for continuous functions. So let me formulate that property or that statement. It is proposition 712 that is the following. Let you have now psi epsilon be a family of random variables or in that case random functions in C0. Sometimes people say random elements in C0 team. If they exist, now positive constant, as before, lambda positive, kappa positive, but now you need also to have some Hölder exponent, so it will be gamma positive, such that for every s comma team from 0 team with s less than team and epsilon positive, you can control the expectation of e to the power lambda divided by epsilon. Let's see, it is like before, but now you write psi epsilon t minus psi epsilon s divided by t minus s to the power gamma. And that is less or equal than kappa 1 over epsilon. Then the family psi epsilon is exponentially tight. Is x tight in the space of continuous functions on 0t. And the proof of this proposition, we will not discuss the proof of the proposition. I propose for you just to prove it, but here I will give you some also reference where you can go to some paper where some property which is needed for the proof is discussed, and then using that property you will be able to prove the exponential tightness. You need to see, let's write that proof that use. And that is corollary 7.1 from the paper, Shields paper from I'm sorry, sheet paper. I hope that my pronunciation is correct, Alexander Sheet. And the paper is called the moderate deviations and functional law of iterated logarithm for super Brownian motion from 1997. You will see the precise, you will find the precise reference in the lecture notes. And then using that corollary, you will see that actually controlling this exponent, you will be able to control the probability that the Hölder norm is larger than some constant. But since the Hölder norm, since the compact sets on the space of continuous functions, you can define via Hölder norm, then it is enough to show the exponential tightness. But today I want to use that proposition to show that the Brownian motion is exponentially tight. But you should pay an attention on that statement, because this statement is useful not only for the Brownian motion, it is also useful when you want to work with any family of continuous processes and when you want to prove the exponential tightness, because you see that for the exponential tightness, in this case, everything what you need to control just some exponential moments of the increments of your process. And in many cases, for instance, if your process is a solution to some stochastic differential equation, also the control, this control can be more or less easily obtained. Oh, therefore, this statement also has an independent interest if you work in this field. And now let's show that for the Brownian motion, we can find that constants lambda, kappa, and gamma for which that inequality is satisfied. It is not complicated to do. And that will be formulated as a lemma. Lemma 713 is let Wt be a standard Brownian motion, or maybe we will not put, all assumptions. We know what is W epsilon, and let's say that just W epsilon is exponentially tight in C0, 0, and proof. We will check, actually we will try to control that exponent, and first of all note that the W t minus W s, you remember that W epsilon, it is square root epsilon W, right? So, and W, it is a Brownian motion. So the Brownian motion has a normal distribution with expectation 0 and variance t minus s. And then it is very easy, and you can do that later, for instance, or maybe you know that already, that you can easily compute the e to the power alpha of the normal distributed random variable, Wt minus Ws. Because you know the density, and then you can see that this expectation, it is equal to e to the power alpha square divided by 2 t minus s. I mean, at this, if you would have here I, then you would have here minus. So because it is a characteristic function, but okay, but now you don't have the I, so therefore you will have no I squared. That also is the reason why you should believe that this formula is correct. So this is for every alpha from R, right? And also s less than q. And now let's consider the estimate, the expectation of e to the power alpha, and then you see that you need to choose this lambda and you need to choose this gamma. At the moment, I do not know what they are, but I want to consider that Brownian motion, like the increments of Brownian motion, absolute value, and then I want to put probably some alpha, where this alpha I will later choose by such a way that I will get this type of the inequality. And then let's do some computations to see what we will obtain. Oh, let's write here. It is square root epsilon, because we want to work with W epsilon, Wt minus square root epsilon Ws. You have the absolute value. So therefore, either you do the computation for absolute value of e to the power, or you that also it is a a possible way, but here we will estimate this one, I mean this exponent as follows. I will estimate that exponent by e, the expectation to e of alpha square root epsilon wt minus square root epsilon. Maybe this square root epsilon I will put outside of the bracket, ws, plus the expectation of e to the power minus alpha square root epsilon wt minus ws. Right? So you can do that for every omega. So I mean, for every omega, you have here the absolute value. And therefore you say, okay, this is, or I mean, you have this exponent. And then for this omega, you can have two possibilities. Either this bracket is positive, and then this expectation is exactly equal to that, or it is negative, and then it will equal to that. So in both cases, you can estimate this exponent by the sum of two exponents. And now you see that here you actually have the minus, but but when you compute that expectation, here you have the square. So therefore, this minus doesn't play any role, and you can say that it is equal to 2 times, and then e to the to the power alpha square. Then you have square root epsilon square, that is epsilon square, divided by 2 t minus s. And then let's take, for this specific epsilon, t and s, let's take alpha, that is equal to square root 2 divided by epsilon square root t minus epsilon, t minus s. And then we get that that the expectation of e to the power square root 2 epsilon, and then you have the absolute value square, I will have here w epsilon t minus w epsilon s divided by square root t minus s. It is less or equal than 2 epsilon, and then when you take, so when you put here square, you will have here square. So therefore you have here square, and here square. And when you take this object and put it here, you see what happens. You will have 2 here and 2 here. They will be cancelled. You will have t minus s in the denominator and t minus s in the numerator. It will be cancelled. And then you will have epsilon square in the denominator and epsilon here. So therefore, everything, what you will see, it will be 1 over epsilon. And of course, it is less or equal for, but actually we need to care for epsilon small. It is less or equal than 2e to the power 1 over epsilon. That implies, for instance, when epsilon is between 0 and 1. And this implies the exponential tightness. And this proves the lemma and also finish the proof of the Schilder theorem. Because having the exponential tightness plus weak large deviation principle, we will get the large deviation principle, the full large deviation principle for the Brownian motion. Okay, we finish the proof, and today I don't want to start the new topic. Next time we will talk about the contraction principle. We will talk about the following nice property of large deviation principle. If you have your random variables or family of random variables which satisfies the large deviation principle, then it turns out that taking a continuous function and considering the function of your random variable, the composition, it will also satisfy the large deviation principle. And you know precisely what the rate function is. So it is very powerful method to prove the large deviation principle, because often you can prove the large deviation principle for, or you can have the large deviation principle for one object, and you can know that actually objects that you are interested in can be obtained as function of the objects for which, or as some transformation of objects that you have already. And therefore, you just can get the large deviation principle for this family that you are interested in via the contraction principle, just via the large deviation principle of another object. We will discuss this more precisely, and in particular, we will apply this, the contraction principle, to the solutions of the stochastic differential equations. Because actually, you can think about stochastic differential equations as some transformation of the Brownian motion. And since we have the large deviation principle for Brownian motion, we also using contraction principle, we will obtain the large deviation principle for solutions to some stochastic differential equations, almost for free. And also a few words about the proof that we finished today. When you go to the literature about the large deviation principle, and you will see the proof for large deviation principle for Brownian motion, you will see a different proof. Usually you will see the proof where you do the approximation of Brownian motion by a random walk, and then having the large deviation principle for random walk, you get the large deviation principle for Brownian motion. But this technique that I showed you, it is more universal. Because, for instance, this technique can be nicely applied, for instance, to some stochastic differential equations with discontinuous coefficients. It could be also applied to some kind of stochastic differential equations in infinite dimensional spaces. Moreover, the coefficients could be also discontinuous, and so on. So therefore, also, I would recommend you to pay more attention to that proof, and probably in the future, when you work or when you prove the large deviation principle for the family of processes that you consider, you also need to remember about this approach, because it can happen that this approach also can work in the situation that you consider. Okay, it is everything for today, and thank you so much for your attention.